Let's have a crack at the following question. Part A starts with state what is meant by an electric field. So electric field is a quantity which is equivalent to an electric force where one of the charges, that is a source charge, is real and the other charge, which is the test charge, is imaginary. Let me explain or expand on that. Electric field is defined as the region around a source charge where an imaginary test charge experiences a force. Electric force is between two charges, let's assume a source charge capital Q and an imagined test charge at a point small q. These two charges would either attract or repel each other by a force F, which is equal to K capital Q small q over r square. If the charge small q is assumed to be a unit positive charge, then the formula for force becomes K into capital Q over r square, which is also the formula for field. So electric field E is defined as the region of space around a source charge where an imagined test charge experiences an electrostatic force. We can also use this to derive an expression between electric field and electric forces. Electric field E is equal to force F divided by the test charge Q test. Moving ahead, an isolated solid metal sphere has a radius capital R. The charge on the sphere is plus Q and the electric field strength at its surface is E. On the figure, draw a line to show the variation of electric field strength with the distance x from the center of the solid sphere for values x, where x values range from 0 to 3 times r. So here we have a solid sphere. So we are supposed to find the electric field where the radius of this is r. So when we started x equal to 0, that is the center of this solid sphere, we understand that until we get to the surface, that is until the value of x reaches the value of capital R, the electric field strength E is going to remain 0. This is particularly because the charges are present on the surface and not within the sphere. And since the total charge contained within the sphere Q is 0, the electric field strength E within the sphere is also 0. So the values are going to practically remain at 0 until we reach R, where it reaches its maximum value, E. Now, moving ahead, electric field E has an inverse square relationship with R, which is given by E proportional to 1 by R square. So for x equal to 2R, let me rewrite this as 1 by x square, since x is a variable. And for x equal to 2R, you have E equal to 1 by 2R the whole square, or 0.25 times 1 by R square, or the value of E is 0.25 times its original value at this point. Let's call it E1. So at 3R, it'll just be E3 is equal to 1 by 3 square, which is 9, which is 0.11 times the value initially. So at 2R, it's going to be approximately 0.25. At 3R, it's going to be approximately 0.11. So here we have an exponential decay graph, which predicts the same. This predicts the exact nature of their relationship, that is E proportional to 1 by x square. Moving on to the last part. The sphere in B has a radius r equals 0.26 meters. So the last part, part C, we have r is equal to 0.26 meters. The maximum electric breakdown occurs when the electric field strength at the surface exceeds a maximum value of 2 into 10 to the power of 6 volt per meter. Determine the maximum charge that can be stored on the sphere before electrical breakdown occurs. So as we've discovered here, the formula for electric field strength in terms of a source charge which produces the field can be written as E is equal to kq over r square, where k is a proportionality constant, which is abbreviated as 1 by 4 pi epsilon naught, and its value is taken from the data booklet as 9 into 10 to the power of 9 Newton meter square per Coulomb square. So when substitute the values for K, E, and R, we get the value for charge Q to be approximately equal to 1.5 into 10 raised to the power of -5 Coulomb.